Okay, in today's video, we're going to be talking about Pascal's triangle and actually how it relates to something called binomial expansion. And binomial expansion is something that you've done ever since Algebra 1 when you first learned how to FOIL out binomials. So it's nothing new. But pretty much today's lesson is actually going to be a shortcut for binomial expansion. And we start out talking about Pascal's triangle to introduce you to this shortcut. And here's what Pascal's triangle is. It says Pascal's triangle was a pattern of numbers that was discovered in the 13th century. Each number in Pascal's triangle is the sum of the two numbers diagonally above it. All outside numbers are 1. Notice here, and that's all these numbers out here. So what they're wanting us to do here in this first example is to simply complete the table here, or complete Pascal's triangle. And you notice again, all these outside numbers going down through here are always 1 in Pascal's triangle, as with these numbers here as well. And then to find any other number like the 2 here, what you actually do is you add together the two numbers that are above it. Like if I add together 1 and 2, it gives me this 3. If I add together 2 and 1, it gives me this 3. So therefore, in order to find this number that goes in this first box right here, we simply add the two numbers above it, which are this 1 and this 3, which will give us a 4. Add together 3 and 3, it would give us a 6. Add together 3 and 1, and it would give us another 4. The last row, row 5, and I do want to point out the first row we call row 0, and that's going to become important here in just a second. But to find this number, we're going to add together the 1 and the 4, and that's going to give us a 5. Add together a 4 and a 6, and that gives us a 10. Another 6 and 4 would give us another 10, and a 4 and a 1 would give us another 5. And we could continue on with another row. We'd have a 1, a 6, 1 and 5 would give us a 6, 5 and 10 would give us a 15, 10 and 10 would give us a 20, 10 and 5 would give us another 15, 5 and 1 give us a 6, and then another 1. We could continue this pattern on and on and on. And what I've actually done is I've downloaded a picture of the first 11 rows. Notice again, we start with row 0, the first 11 rows of Pascal's triangle, and you just continue on. And any of these numbers can be found by just simply adding the two numbers above it. 20 and 15 here would give you a 35, or a 70 and a 56 would give you 126. And notice the numbers get larger and more complex as we work our way down. But again, that is Pascal's triangle. Now, I actually want to take and I want to relate that to another concept that we've actually already talked about. And this is where things get a little bit odd, is let's go back and let's talk about combinations for just a second. And let's start out with just a reminder of how to find a combination. Let's do the combinations of 2, choose 1. Well, let's do something a little bit more complex than that. Let's do the combinations of 4, choose 3. Again, the second number tells you how many choices that you're making, so you'd have 3 blanks. There are 4 things to choose from, so we'll have 4 choices, 3 choices, and then 2 choices. And since it is a combination, you'll always divide by whatever number that you're, however many you're choosing, factorial. So here we're going to be dividing by 3 factorial. So that would be 4 times 3 times 2 divided by 3 times 2 times 1. These will cancel out, and it leaves us with 4. Okay. Well, what I want to do now is I actually want to finish out, and I want to do a few more combinations. The combinations of 4, choose 3 we just found out was 4. The combinations of 4, choose 2. You could follow a simple, another, the same strategies. You'd have 2 blanks. That'd be a 4 times a 3 divided by 2, and I believe you'd get a 6 there. I want to do, let's do the combinations of 4, choose 1. That would be, hang on just a second. Combinations of 4, choose 1 would be one blank with 4 to choose from, and then divided by 1 factorial, so that'd be a 4. The combinations of 4, choose 0. There's only one way to make a choice of 0. Let's do the combinations of 4, choose 4. That'd be 4 choices, 4 blanks. That'd be 4 times 3 times 2 times 1 divided by 4 times 3. So that would also be 1. And I want to relate these numbers. Look, 4 choose 4 is 1. 4 choose 0 is 1. 4 choose 1 was 4. 4 choose 2 is 6. I want to relate that to something. Look at row 4 right here. Notice these numbers 1, 4, 6, 4, and 1. These rows of Pascal's triangle actually also correspond with the different choices that you can have if you're choosing from 4 different things. The combinations of 4 choose 1. The combinations, or excuse me, 4 choose 0. The combinations of 4 choose 1 was 4. The combinations of 4 choose 2 was 6. The combinations of 4 choose 3 was 4. The combinations of 4 choose 4 was 1. So if we actually went through and I needed to know, let's do a combination with 5. Let's do 5 choose 3. That'd be 3 blanks. That'd be 5 times 4 times 3 divided by 3 times 2 times 1. 3 cancels with 3, 2 cancels with 4. That gives me 10. Or I could just do it this way now. The combinations of 5, since I'm choosing from 5 things, look for row 5. Choose 0, 1, 2, 3. The combinations of 5 choose 3 is right there. It's the exact same answer that we got before. So not only does Pascal's triangle, it's just this row of or pattern of numbers here, but it actually also corresponds with combinations. The combinations of choosing from different numbers of things. So now let's talk about binomial expansion, and we'll go back to Pascal's triangle here in just a second. But expanding a binomial, let's take the binomial a plus b to the third power and just remind you that to raise a plus b to the third power, we're actually going to have to do a plus b times a plus b times a plus b. You cannot just raise each of these to the third power. You do have to FOIL this out. The way that we're going to do that, you'd multiply 2 at a time. So that's going to be a times a is a to the second. A times b is ab. B times a is also ab, so that'd be 2 ab's. And then b times b would be b to the second. Then you have to multiply that by a plus b again. And you would get a to the second times a would be a to the third. A to the second times b would be a to the second b. Done with a to the second. 2ab times both of them would be 2ab times a would be 2a to the second b. 2ab times b would be 2ab squared. That's 2ab squared. And then b to the second times a would be ab to the second, and b to the second times b would be b to the third. Combine some like terms here. I get a to the third. A to the second b would, those two would combine, that'd be 3a to the second b's. So we're done combining those. Combine these, that'd be plus 3a to the ab to the second, and then plus b to the third. And I want to point this out now. Look at the coefficients. What do you notice about the coefficients? 1, a to the third, 3, a squared b, 3ab squared, and plus 1, b to the third. Let's go back up to Pascal's triangle, and let's point out this row of Pascal's triangle. 1, 3, 3, 1. When we raise this to the third power, notice that we get for coefficients 1, 3, 3, and 1, which is just like the third row of Pascal's triangle. And there is a reason for that connection. And here's what it is. The binomial theorem says, and notice the combinations here, that if you're wanting to raise something to some nth power, this could be the third power, fourth power, fifth power, well, whatever power, here's all you have to do. Combinations, the combinations of n choose 0, n choose 1, n choose 2, n choose 3, pretty much is telling you the coefficients are going to be the same as they are in Pascal's triangle. And then what do I do for the a's and b's? And I'll show you on these next couple of examples what you can actually do there to make it a little bit easier. But the biggest thing you need to know right now is to raise it to the fifth power. All we've got to do is come up here and let's take our fifth row. And these numbers right here will be the coefficients for our expansion. We don't have to go through all this trouble of foiling stuff out anymore. So what we're going to do to raise a plus b to the fifth power, step one, take the numbers in those rows. 1, 5, 10, 10, 5, 1. And let's write them down. 1, is it 1, 5, 10, 10, 5, and 1. Okay, and all those were positive numbers, so if you'd like to put your plus signs in front of them, that'll be good. Okay, now here's what we're going to do with what does this whole a to the n and b to the 0 and all this means? What you're going to do is you're going to take your first value right here, the first part of your binomial, and you're going to raise it to this power. You're going to have an a to the fifth, and then you're just going to count down a to the fourth, a to the third, a to the second, a to the first, and you don't have to put that 1, and then a to the 0. And what a to the 0 means is you don't have to put, there's no a's there. You don't have to put the a's. Then you're going to take the second value, this positive b right here, and you're going to raise it to the 0 power, and we're going to count up now instead of counting down. So b to the 0 power right here, you don't have to put. Then we're going to do b to the first, we're going to do b to the second, b to the third, b to the fourth, and b to the fifth. And let's clean that up a little bit. 1a to the fifth is just simply a to the fifth. Then you have 5a to the fourth b plus 10a to the third b squared plus 10a to the second b to the third plus 5ab to the fourth and then plus b to the fifth power. This is the expansion that you would get by doing a plus b to the fifth power, which is so much easier. That would have took us all day to sit and actually multiply that out. Okay, for the seventh power, now our table only went up to, we did row 5 here, and then we did a row 6, but I need to a seventh power. So what I did, again, I've got Pascal's triangle here, so I'm going to pick row 7 here. It's always easy to figure out which one row 7 would be because the second number right there would be a 7. If you want to raise something to a second power, you'd use this. To a third power, you'd use this row. To a fourth power, you'd use this row, and so on and so forth. But I just need my numbers in my seventh row, which is 1, 7, 21, 35. And notice the symmetry there. 1, 7, 21, 35, and then it just counts backwards. So let's go back. 1, 7, 21, 35. And is that right? 1, 7, 21, 35. And then I have 35, 21, 7, and 1. And all those numbers were positive, so if you'd like to put plus signs in front of all of them, just so you have that to separate your terms in this sequence. And then again, you just simply start with your first value, and you're going to raise it to the seventh power. Where do I get that seventh power? Is right here. And then you just count down: sixth, fifth, fourth, third, second, and first. And then you will have no x's here. Then you'll go to your second term, which is this positive y, and you're going to start with 0 here. There's not going to be any. Then you'll go y to the first, y to the second, y to the third, y to the fourth, y to the fifth, y to the sixth, and y to the seventh. And that will be your binomial expansion for x plus y to the seventh power. Let's do one more of these. C plus d to the 10th power. Now we're going to have to go way down on our triangle for this one. We're going to have to use this very last row right here. So 110, 45, 120. So we've got a 1, a 10, a 45, a 120, and I believe the next one was a 210, a 252, a 210, and I believe I'm going to run out of room. So let me pause and move my numbers over. Okay, there we go. I've got all my numbers, and I went through and I put all my plus signs because all of them were positive values. So now all I've got to do, since I'm raising it to the 10th power, take your first number, We're going to start with c to the 10th, c to the 9th, c to the 8th, 7, 6, 5, 4, 3, 2, and 1. And then you take your D's, and you can either start at the end and count up, or you can start at the front and or start at the end and count down, or start at the front and count up. So have 0 D's, then you have 1 D, 2 D's, 3 D's, D to the 4th, D to the 5th. And as I go along with this, I want you to notice the powers in each group. D to the 8th, D to the 9th, and D to the 10th power. And there's your expansion. But notice the powers in each group. Point something out. You have 9 C's and 1 D. You have 8 C's and 2 D's. You have 7 C's and 3 D's. Notice that you're raising everything to the 10th power, and that will always fall true. Here you have no D's. There's D to the 0 there, and it falls true there as well. And that's always going to be the case. Okay, now what if we're raising something to a power that has a number in it? Okay, we're going to start these problems the exact same way, x minus 3 to the 6th power. These are going to be a little bit tougher, but not too bad. So we need a 6th power, so we're going to go back to our Pascal's triangle, and the 6th was that bottom row that we created, which was 1, 6, 15, and 20 was the numbers we need. So 1, 6, 15, and 20, and then we count back down, 15, 6, and 1. And we do the exact same thing. Those were all positive numbers, so we put our plus sign here. Now that'll change in just a second with something else we've got to do. We start with our first number and we raise it to the 6th power. So we're going to x to the 6th, x to the 5th, x to the 4th, x to the 3rd, x to the 2nd, and x to the 1st. But then notice our second term is a -3. So we have -3 to the 0. And we haven't been putting that. So we have -3 to the 1st, -3 to the 2nd, -3 to the 3rd, -3 to the 4th, and we're just going to have a little bit of cleaning up to do here. -3 to the 5th power and -3 to the 6th power, because now we got to go another step. We've got to clean each term up. So my first term was 1x to the 6th. My next term, I have a +6 and a -3 to the 1st, which can now actually be combined. A +6 times -3 would be a -18 x to the 5th. -3 to the 2nd power is 9, so I have 15 times 9, which is a +135 x to the 4th. -3 to the 3rd power is a -27. I have a +20 times a -27, which is a -540 x to the 3rd power. -3 to the 4th power is 81, and I also have a +15 in that term, and 15 times 81, I'm going to have to multiply those out. 15 times 81 gives me a 1,215, so positive 1215 x to the 2nd. -3 to the 5th power is a -243, and I've got to multiply that by the 6, so that's going to give me a -243 times 6, 1,458 x to the 1st. And then finally, -3 to the 6th power gives me a +729. So with those problems, we have just one extra step, but the process is the exact same. Number 5, erase that. We're raising this stuff to the 7th power. So we need the 7th row. Again, reminder that the first row is a 0 row. So we need the 7th row, which is this row here. 1, 7, 21, 35, and then the same numbers backwards. 1, 7, 21, 35. So let's write those numbers out. A +1, a +7, a +21, a +35, and then the same numbers, 21, 35 first. positive 21, positive 7, and positive 1. I ran out of room there. Let me again pause this and spread those out a little bit. Okay, now there's our different numbers. And again, we do the same thing. We start with our first term of the binomial. We're going to raise that, and I'm going to put in parentheses a 2m to the 7th, a 2m to the 6th, and a 2m to the 5th, 2m to the 4th, and this will require just a little bit of cleaning up at the end, 2m to the 3rd, 2m to the 2nd, and 2m to the 1st. Now we start with our second term, which is a positive n, and we're going to raise it to the 0. We have n to the 1st, n to the 2nd, n to the 3rd, n to the 4th, n to the 5th, n to the 6th, and n to the 7th. And now the rest of it is cleanup. Reminder that to raise 2m to the 7th power, there's no plus signs there. We can just simply raise each of those to the 7th power. So we're going to have 2 to the 7th, which let me multiply that out. Which is 128. So we have 128, and we also have m to the 7th, which is just simply m to the 7th. Our second term, we have 2m to the 6th. And don't forget, not only do we have 2 to the 6th, but we also have to multiply that by this plus 7 out front. So we have 2 raised to the 6th power, and then times 7 gives me 448. So a positive 448. Now we also have to raise m to the 6th and the n, plus we have 2 to the 5th, m to the 5th, and then 2 to the 5th power is equal to 32, but not only that, but we have to multiply 21 times that, so times 21. So 672 m to the 5th, n to the 2nd. See if this makes things a little bit easier. To raise 2m to the 4th power, I'm just going to write the answer above it. 2 to the 4th would be a 16, and m to the 4th is simply m to the 4th. So we now have 35 times 16m to the 4th. So 35 times 16 gives me plus 560 m to the 4th, n to the 3rd. 2m to the 3rd power is 8m to the 3rd. So we have 35 times 8m to the 3rd. 35 times 8 gives me 280. So plus 280 m to the 3rd, n to the 4th. Plus 2m to the 2nd is 4m squared. So you have 21 times that, which would be a plus 84 m squared, n to the 5th. We can now do these in our heads. 7 times 2 is a 14 m, n to the 6th, plus n to the 7th power. There's your expansion there. The next two would be done the exact same way. I will jump down here and we'll work number 7 together. It looks like a little bit more difficult, but number 6 would be worked identical to it. It's just like the previous examples. But let's try this one. The 5th power, that is one of our rows that we had up here. So let's scroll back up and find the 5th power. That's 1, 5, 10, 10, 5, 1, so a little bit smaller. But I am going to leave me plenty of room here. 1, 5, positive 5, a positive 10, positive 10, positive 5, and a positive 1. Just because this one's going to be a little bit uglier because you've actually got two different values. Instead of just plain P's and Q's, you've got uglier values in both of them. So we start here and we have 3p to the 5th, 3p to the 4th. Oops. Let me erase that. That whole 3p is being raised to the 4th power. We have 3p to the 3rd, 3p to the 2nd, and 3p to the 1st. Then you go to your negative 2q and you count down count up negative 2q to the 0, negative 2q to the 1st, negative 2q to the 2nd, negative 2q to the 3rd, and negative 2q to the 4th, and finally negative 2q to the 5th. Now I do want to point out your powers. The fifth power, the fourth and first adds up to 5. 3 and 2 adds up to 5. 2 and 3 also adds up to 5. So we've got those right. Okay, let's start with our first term, which is simply 5p raised to the fifth power. So we just raise both of those to the fifth power. That's easy enough. So that's going to be, and I'm going to skip up here above and write my answers, final answers up there. 5 raised to the fifth power, that's going to be 3,125 p to the fifth. And the reason I'm giving myself plenty of space is right here above, I'm going to write these out. 3 to the fourth, I have, well, first off, my 5. 3 to the fourth was 81 p to the fourth. And then raise both of these to the first power gives me times -2q. So I got to do 581 and -2. That's going to give me a negative value. That's going to be -810 p to the fourth q. So we're done with those two sets of parentheses, or two terms. Here I have a 10. 3 to the third is 27p to the third. Then -2 to the second would be a +4q to the second. We've got to do 10 times 27 times 4. I believe that's a and that's a dot. That's a multiplication. That's plus 1080 p to the third q to the second. Here I have a 10. 3 to the second p to the second is a 9p squared. -2 to the third is a -8 q to the third. So I'll do 9 times -8 is -72 times 10 is -720. That's a bad zero. I had 2 p's and 3 q's. 2 p's and 3 q's. Done with that term. Let's see. Now I have a 5. 3p is to the first power. And then -2 to the fourth, that would be a +16q to the fourth. So I have 3 times 16 is 48, times 5 is 240. P to the first, Q to the fourth. And then finally my last term, -2 to the fifth power. That's going to be a -32p to the fifth power, and there is your expansion. So that was a little bit tougher. Okay, now some observations. Let's fill out this observation form that we've noticed from each of these. The total number of terms is always, I don't know if you noticed this, but here we raise this to the fifth power, and I want you to count. We had 1, 2, 3, 4, 5, 6 terms. The seventh power, we had 1, 2, 3, 4, 5, 6, 7, 8 terms, excuse me. Sixth power, we had 7 terms. So notice that if we're raising something to the nth power, the number of terms will always be n plus 1. You'll always have one extra term. The exponent of a in the first term is. So whenever you start with a, you always start and you do a to the nth power, and then you count down from that. So the actual exponent, let me reread the question. The exponent of that a term will always be n, and then you count down. The exponent of the b term, of the b in your last term. So that would be like if we scroll up here, the exponent of my b here in my last term was b to the fifth, because we start with 0 when we count up. So that is also n. Is also n. The exponent of a blanks from left to right. So we always start with the nth term, n for my first term, and the exponent of a decreases by 1 from left to right for each other term. The exponent of b increases by 1 from left to right. And we also know that we start with the 0 term there as well. The sum of the exponents in each term, I pointed that out a while ago, to where, like here, at a 7th power, a 6 and a 1 power, a 5 and 2, a 4 and 3, a 3 and 4, a 5, 2 and 5. Why? Because we was raising it to a 7th power. So if we're raising something to the nth power, the sum of the exponents will always be n. The coefficients are blank and follow the blank row of blank. And that's a little confusing. That's nearly one too many blanks. The coefficients are always, what they're looking for here is they're symmetrical. The coefficients, when we start our problems, are always symmetrical. We go back up and look at it, like here, 1, 10, 45, 120, 210, 252, and then we have the same numbers counting down. So the coefficients are always symmetrical, and the way that we get those coefficients are, and they follow the nth row of Pascal's triangle. So we see a very, very useful application for Pascal's triangle. And oddly enough, this is not the only application for Pascal's triangle. It appears so much in several different things that we can be doing through our advanced math courses. So it's very important to us.